As we continue our discussion of stereochemistry, we want to talk now about the term chirality. Chirality is a subset of stereochemistry, and it deals with only those molecules that rotate plane polarized light. So it's a property of molecules that can rotate plane polarized light. And this is actually different from stereoisomers that cannot do so. So the examples of stereoisomers that cannot rotate plane polarized light are the geometric isomers. But a molecule is considered chiral if it can rotate plane polarized light. If it's chiral, it will always possess a non-superimposable mirror image. And so it can rotate plane or circularly polarized light and while we might not be able to predict that particular property, something that is chiral will always possess a non-superimposable mirror image. The most common types of examples of chiral molecules are those that contain a stereocenter. So a stereocenter, also known as a stereogenic center, or a chiral center, these are all synonyms. A stereogenic center is a tetrahedral atom that contains 4 different groups. This means that the molecule itself has a non-superimposable mirror image, or enantiomer. So let's take a look at some examples. So if we took this molecule here, so this molecule has defined a stereochemistry at the tetrahedral carbon labeled with a red star. Right? It has a non-superimposable mirror image because if we were to draw the mirror image of that molecule, it would look something like this. And that molecule is not superimposable upon the first one, so we say that these two molecules are enantiomers, and therefore the first molecule is indeed chiral. This molecule has a non-racemic stereocenter at the starred carbon. It has is a tetrahedral carbon that has 4 different groups attached: an isopropyl group, an amino group, a methyl coming towards you, and a hydrogen going back away from you that is not drawn in. Another example of a stereocenter would be an ammonium ion. And so we have a methyl group, a phenyl group. Phenyl is just short for a benzene ring. We also have a benzyl group, which is a CH2 in between that and the benzene ring, and then an ethyl group. So overall, the nitrogen is positive, but we say that that nitrogen atom is a stereocenter because it's a tetrahedral atom that contains 4 different groups in a spatial arrangement. If we were to draw the mirror image of that, it would be non-superimposable upon the first. We have to be careful, though. We need to make sure that it has defined stereochemistry. And so this molecule here is a racemic mixture, because I haven't defined the stereochemistry at the stereocenter. So even though this is a stereocenter, it is a racemic stereocenter. And so molecules that are chiral have to contain a non-racemic stereocenter, which is the first example that we did. So this is a racemic stereocenter, and so we say that this is overall achiral, not chiral. It is a mixture of the wedged methyl group and the dashed methyl group. Now, a molecule that contains a stereocenter can be considered chiral, but this is not always the case. So we have a couple of examples where molecules contain stereocenters, but they are overall not chiral. These molecules might be diastereomers because they are non-superimposable, non-mirror image isomers, but only a few of them could be chiral. So, for example, let's say we had this molecule here. And we have this molecule here. You would agree that there are stereoisomers of one another, and it turns out that they're diastereomers of one another. These are non-superimposable, non-mirror images of one another. Now, each of these diastereomers, we need to determine whether or not they are chiral or not. So in order to determine whether or not they are chiral, the first thing we do is determine whether or not they are non-superimposable, whether or not they have a non-superimposable mirror image. So we can draw the mirror image of this one and see if it can superimpose upon the first one. And so we have the OH going back, we have the OH moving forward. And indeed, when you take a look at this molecule and you try to superimpose it upon the first one, you can rotate it 180 degrees clockwise, and the OH group that's on the bottom will become the top OH group, and it will be a wedge, which is in the exact opposite direction of the OH group in the first molecule, which is a dash. Likewise, the OH group that's a dash will go from the bottom, from the top to the bottom, become in the exact opposite direction of the OH group that's a wedge in the first molecule. So that tells you that these two molecules are non-superimposable mirror images of one another, so they are enantiomers. But it also tells you that the first molecule here is chiral. Okay, we have defined stereochemistry. We have two stereocenters here and here, and so this molecule has stereocenters and is chiral. It is chiral because it has a non-superimposable mirror image. Now, it is also true that this molecule, the diastereomer, also contains stereocenters. Each one of those red carbon atoms is a stereocenter. It's a tetrahedral atom with 4 different groups on it. But we need to determine whether or not this molecule is chiral or not. And so we need to draw its mirror image and try to see if we can superimpose that mirror image upon the first one. And so the mirror image looks like that. And now when you rotate that 180 degrees clockwise, you will see that all of the groups will superimpose upon the first molecule. And so this is a superimposable mirror image, and so therefore those are the exact same molecule. And so by definition, that first molecule is achiral because it does not contain a non-superimposable mirror image. We say that overall it is a molecule that has stereocenters but is overall achiral. Now the reason for this is because it has an internal plane of symmetry. And so the internal plane of symmetry goes directly through the carbon-carbon bonds of the ring. And you can think about it as sort of the top half of the molecule rotating plane polarized light to the left, and the bottom half of the molecule rotating plane polarized light towards the right, or vice versa. And those two things will cancel one another out. And so overall, the optical rotation will be 0. And this is the reason why it's achiral. It does not rotate plane polarized light. And so we have a special name for these types of molecules that have stereocenters but have an internal plane of symmetry. And these are known as meso compounds. And so meso compounds have stereocenters, but are overall achiral because they possess an internal plane of symmetry. Now, there are also molecules that exist beyond the sort of traditional description of a tetrahedral atom bearing 4 different groups. So let's take a look at that. So this is chirality beyond the sort of typical carbon stereocenters. And we actually already referenced one of them already, which was the ammonium ion. Remember that the only real descriptor for a molecule that is chiral is one that has a non-superimposable mirror image. And so we can have all sorts of molecules that don't have carbon in them as their stereocenter that have non-superimposable mirror images. So, for example, this phosphine oxide. This phosphine oxide has a phosphorus-based stereocenter, and if you were to draw the mirror image of that molecule, you would not be able to superimpose it on the first molecule, and so therefore it possesses a non-superimposable mirror image, and so we say that this molecule is chiral. Another example would be the sulfoxides. So sulfoxide has a lone pair going back and an oxygen bearing a negative charge, negative formal charge going forwards. The sulfur is overall positive. Okay, we say that the sulfur is a stereocenter and it possesses a non-superimposable mirror image, and so we say that that molecule is overall chiral. We also had the example that we did before, which was the chiral ammonium ion. So nitrogen overall has a positive charge, and this is spatially arranged in a defined manner. We have dashes and wedges indicating the stereochemistry. This has a non-superimposable mirror image, and so therefore it is also chiral. So the phosphorus, the sulfur, and the nitrogen here are all examples of stereocenters. Now, one big caveat here is that not all things that contain 4 different groups, not all atoms that contain 4 different groups are chiral. And the best example of this is not the ammonium, but the amine group. And so the amine group is as follows. So I could draw a trigonal planar atom that looks like this. Trigonal pyramidal atom that looks like this, in which I have the lone pair sort of sitting at the top of that trigonal pyramid. Now, it turns out that this particular molecule is achiral, and the reason is that it typically inverts the pyramid rapidly. So I have a defined stereochemistry for this pyramid. I've got the lone pair and the ethyl group sitting in the plane of the page, the methyl group pointing back, and the isopropyl group pointing forward. But at room temperature, this particular configuration actually inverts so that the lone pairs actually go down. So you'll have a nitrogen lone pairs on the bottom, ethyl group here, methyl group here, isopropyl group here. And so those two things are going to be in equilibrium with one another. So you can't ever sort of isolate an individual trigonal pyramid which has defined stereochemistry. And so we say that nitrogens, in this case nitrogens with lone pairs, we say that those atoms rapidly pyramidalize. And because they rapidly pyramidalize, you can't ever have a single chirality. And the reason is because when you convert one pyramid to the other, these two molecules are enantiomers. And so you destroy any chirality that you initially had with that a specific arrangement of atoms. And so the barrier to pyramidalization here is quite low, and so you can't ever isolate a single enantiomer. Now this is different from phosphines. Phosphines do not rapidly pyramidalize, and so you could have a phosphine that has the same kind of groups attached to a phosphorus with a lone pair, and this molecule is completely stable. It does not rapidly pyramidalize, and so we say that it has a non-superimposable mirror image, and therefore it is chiral. Now there are other molecules that are chiral, even though they don't contain any stereocenters at all. So let's take a look at those. So these are chiral molecules without any stereocenters. Now remember, we said that the major thing that determines whether a molecule is chiral or not is if it possesses a non-superimposable mirror image. So it's not a requirement that it contains a stereocenter. It's just that the molecule itself has a non-superimposable mirror image. So let's see if we can come up with some examples here that fit that description. So the first one are the allenes. So allenes are a class of molecules that have an sp hybridized center, but that sp hybridized center has two pi bonds attached to it. And so it sort of exists like this. So we have a carbon in the center that I'll indicate with a dot. I have one pi bond on the sort of left-hand side of this molecule that's going to express these groups ethyl and methyl in the plane of the page. And so you know that the pi bond is above and below the plane of that CC bond here. But you also know that if it's sp hybridized, that carbon center, then the other pi bond is going to be in front and in back. And so the other two groups that will be on the opposite side will be coming directly out towards you or directly back away from you. This is not up and down, it's directly out towards you and directly back away from you. And so what we can do is we can sort of take a look at this molecule from a Newman projection standpoint, look down the barrel of that bond, and what we'll see is that we have a center, carbon center that has an alpha group pointing up, a methyl group pointing down, and on the back we have a chlorine atom pointing to the left and an isopropyl group pointing to the right. And this sort of gives this molecule a helicity to it. Now this is a form of chirality known as axial chirality. In these molecules, it's as if this sort of central sp3 hybridized carbon has four different groups attached, and you can sort of see that with that Newman projection. So it's a form of chirality known as axial chirality, and the reason this molecule here is chiral is because it possesses a non-superimposable mirror image. So let's draw that non-superimposable mirror image. So here's the original molecule. If I draw a mirror plane here, I've got an isopropyl group coming out towards me, chlorine going back away from me, and then I've got ethyl here and methyl there. And if I were to try to line up the ethyl and the methyl group by flipping this molecule sort of from front to back 180 degrees, the chlorine atom would be facing forward and the isopropyl group would be facing backwards. And so these two things are enantiomers, which means that the first molecule possesses a non-superimposable mirror image, and therefore it is chiral. So allenes is one example of this. Another example of a molecule that is chiral but doesn't have any stereocenters is the helicenes. So helicenes are hydrocarbons that have a twist to them. And similarly, a DNA double helix twists with a certain handedness, so it's also chiral. So if we, for example, look at the DNA double helix, you have something like this, and we say that there are base pairs in between, and that this DNA double helix twists sort of like a candy cane. It twists to the right, and so we say that that DNA is, of course, chiral. It has a non-superimposable mirror image. Same thing can occur with hydrocarbons. And so here's an example of a helicene. You have sort of a flat hydrocarbon. These are mostly sp2 hybridized molecules, atoms, excuse me, like this. Okay. So what happens here is that these two protons that are sitting here and here are actually lying coplanar to one another. So what happens is that one of the two planes cannot, it sort of puckers. You'll have one ring sort of slide up onto on top of the other. And so it's as if this ring is kind of puckering up out of the plane of the page. Forgot my double bond. And this other hydrogen is kind of pointing backwards, or that entire ring is pointing backwards. And so it's kind of like a loop which has a hydrogen pointing here and another hydrogen that's pointing in that direction behind. And so this gives this molecule a certain handedness to it. And so the handedness obviously creates chirality for this particular molecule, such that it has a non-superimposable mirror image. And finally, the last kind of molecule that does not contain any stereocenters, but is overall chiral, are the atrope isomers. So atrope isomerism occurs when there's hindered rotation about a sigma bond. And this is another type of axial chirality. And the examples here are sort of when you have two benzene rings that are sort of connected to one another, but then you have another sigma bond that connects another two benzene rings that are connected to one another. And so this is an example of a binaphthal group. And you'll see over here that these two hydrogens are bumping into one another. So there's a lot of steric clash there. And so what happens is, if we can redraw this, what happens is that one of the rings will sort of lie out of plane, and the other will lie in the opposite plane. And so that reduces the amount of steric strain that you have. So, for example, we have this ring here, which is kind of coming out towards you, or that entire ring is coming out towards you. And then we have this ring here, in which this part of the molecule is coming out towards you. And so these two rings lie perpendicular to one another. And because of those two hydrogens that are bumping into one another, the rotation here is blocked, it's hindered. You cannot fully rotate around that sigma bond. And so there's a hindered rotation. And because there's hindered rotation, we can actually draw the mirror image of this molecule, and it will be non-superimposable upon the first, and so therefore this molecule is chiral. And it's all because of that bond, that sigma bond connecting those two rings, that cannot fully rotate 360 degrees. All right, so let's do another example of this. I'm going to move these over a little bit so we can get some space. One of the requirements for atropisomers is that you have to have certain groups attached. And so let's take a look at this example here. So let's say I have a methyl group here and a chlorine group here, and this is connected to another molecule, but this time that benzene ring is kind of puckered out of plane. It's kind of sitting flat. And then I have a methyl group here. All right, this molecule is chiral, and the reason it's chiral is because it contains a non-superimposable mirror image. The mirror image that we will draw in a second is an enantiomer. And the reason we can't rotate around that sigma bond is because the two chlorines and the two methyl groups will bump into one another when they're coplanar. All right, so one of the requirements for atropisomerisms is that you have to have at least three of the four substituents that are close to that sigma bond have to be substituted. So if I took this green chlorine and I just put a hydrogen there, this molecule will still have a difficult time rotating around that sigma bond. And so you have to have at least three of the four. If I took another one of the chlorines away, if I took the second chlorine away, then it would have no problem rotating 360 degrees. Well, let's get back to why this molecule is chiral. If we were to draw the mirror image of this, it would look something like this. And indeed, this particular molecule, if you try to line up the methyl and the chlorine, atoms of one particular benzene ring, the other one will lie in the exact opposite direction. And so these two groups are enantiomers. They are non-superimposable mirror images of one another, and so therefore they are chiral. And so the best way to determine whether or not a molecule will rotate planes polarized light is to determine whether or not it possesses a non-superimposable mirror image. If it does, the molecule will be chiral, and it will be able to rotate plane polarized light. Some of those molecules do not contain any stereocenters. Those are the atropisomers, the helicines, and the allenes. Others don't contain carbon stereocenters, but contain other types of stereocenters, like phosphorus, sulfur, and nitrogen, with 4 different groups. And then others still will contain a carbon-based tetrahedral stereocenter with defined stereochemistry such that it's non-racemic. It is also true that you will have molecules that are meso, in which they contain stereocenters, but because of an internal plane of symmetry, they are no longer chiral, they are achiral, and they will not rotate plane polarized light.